Thank you everybody for joining us today. We're excited to be able to share some of the research we've worked on really over the last 15 to 20 years. Some of this research goes back. So excited to share some of this data. It's very fitting for the 2050 goals that we set earlier this year as an industry and will really help underpin some of those efforts and help us better understand how to go forward. Joining us today, we've got a couple of staff members with the USDA Ag Research Center in Kimberly, Idaho. They've been a tremendous resource for us over the years, and they'll be taking on much of the presentation to present the data that they've generated in their research projects. We're going to start with a interseeding cover crop in corn project that we just started this year. It's a collaboration with Hegler Creek Dairy, one of our dairymen here in Idaho, and we'll just move into some of the other presentations from there.
Hegler Creek first considered interseeding cover crops in corn when an agronomist suggested it as a great way to stabilize the soil while producing additional livestock feed. They have experimented with it over the last 2 years and have seen positive results. We talked to Kurt Heward, farm manager at Hegler Creek Dairy, to get the inside scoop on their experience cover cropping in corn.
Didn't all work out perfectly at first. It was good enough that we successfully were able to justify it and do it again. It's still an experiment under trial.
Cover cropping can be used to uptake additional nutrients, prevent erosion, and improve soil health.
Our first goal was probably the ability to graze. And then the second, especially on this field here where we have these gullies and elevation differences where we try to help erosion, allowing our water to penetrate better, not run out of our fields.
In order to achieve good seed-to-soil contact, the farmer prepares the field prior to applying on the cover crop seed.
A lot of our fields we do center break or we dam or dike our corn. That's what's needed to actually get the cover crop to establish in the soil.
Hegler Creek wanted to get the cover crop established a little earlier than previous years, so this year they modified their pre-plant tillage practices.
Normally we're waiting until about V6 so we can dam or dike and then put the seed on. This year the corn is as small as it is. We were a little nervous to dam or dike and risk of covering up our corn. Our center breaker is just a lot smaller shank, so we're able to eliminate the risk of covering up any corn.
Once tillage is complete, the cover crop is flown onto the field. Amazingly, seeding an entire pivot only takes about 30 minutes. One of the main concerns with incorporating cover crops is the need for extra water. We asked Kurt how he approaches this challenge.
I do know that the cover crop is taking some water, obviously, but I haven't seen a huge effect on the corn at this time.
Next, we asked Kurt what effects the cover crop has had on the forage quality and yield of Hegler Creek silage corn.
I've probably noticed anywhere from maybe a 3 to 4 at the most ton difference, and then the least is probably a ton, but at least a ton difference of corn drag. But one of the greatest benefits that it does for the corn would probably be quality, and that's because of the dry down that we get at the end of the season. Our cover crop fields would mature much faster and we'd have a way more mature cob, therefore resulting with better quality corn going in the pit.
Not all producers have the ability to graze cover crop for harvest. Kurt discussed the challenges of other harvest methods like green chopping.
We talked about possibly trying to green chop this year. I'm a little concerned on this field mainly because of our mounds on our corn are so big. It's going to be kind of hard. Green chopping would be a nice tool to have. All of our fields aren't easily grazed.
Idaho Dairymen's Association has taken interest in Hegler Creek's experiment and is trying to provide some data and research to show the effects of the cover crop. We want to increase cover crop adoption among Idaho dairymen. We are measuring nutrient uptake, forage quality of both the corn and cover crop, and differences in yield. We look forward to sharing the results in the future.
Does cover crop increase or reduce corn silage yield?
That is one of the parameters that we are looking at with this research project. We don't have any data yet, but we hope to collect that this fall and share it at a later date.
Anecdotally from the farmers that have done it in the past, they've said that they've had slightly reduced tonnage per acre, but the quality of the corn silage, because they get a quicker dry down, far outweighs the loss of tonnage, and you get a benefit to better silage and better feed quality.
Did I miss the type of cover crop, and what did you see?
It was a combination of clover, ryegrass, and 2 different brassicas. It was seeded at 18 pounds to the acre.
How did you terminate the cover crop, and what happens to it? Will it be incorporated?
This particular grower grazes his cover crop, but we are also looking at other methods of harvesting like green chopping.
You mentioned a couple of those cover crops. What are common cover crops for that area in Idaho?
That mixture of the clover, ryegrass, and brassicas, that's pretty common here. They also use vetch and Austrian peas.
We'll move on to introducing Drs. Rob Dungan and April Latham, 2 of the researchers here at the Kimberly ARS Research Center. We're going to go on to our long-term manure study that we've been working on for the last 8 years with Dr. Latham and Dungan.
I'm April Latham. I'm a scientist with the USDA Agricultural Research Service out here in Kimberly, Idaho. And my research program is focused on integrated dairy, livestock, and cropping systems. And where we're at today is one of our long-term studies that we call the long-term manure study, which was a study started in 2012 to look at using manure in a crop rotation that was not typical for a dairy forage production system. So this study has a crop rotation of wheat, potatoes, sugar beets, and barley. And we wanted to look at using manure in these different crops because there are a lot of producers in our area that produce these crops and are a little bit nervous about using manure in these systems because they're worried about issues with disease, crop quality, and in some cases they're really just not sure how to handle the nutrient management when it comes to using manure in the rotation. So this study looks at 3 different rates of manure that we apply either every year or every other year. So we have a low rate of manure that's 15 tons per acre, a medium rate that's 30 tons per acre, and a high rate that's more typical for what we see on lots of dairy producers' fields. It's closer to 45 tons per acre. And we also have 2 treatments, a control and a fertilizer, that show the differences between using strictly fertilizer in your rotation and using manure. And then we're really looking at nutrient cycling within the soils, particularly nitrogen and phosphorus, looking at nitrogen mineralization rates when it's becoming available to the plants, looking at soil cycling of nitrogen and phosphorus, plant uptake, and nitrogen and phosphorus throughout the soil profile. And another important component is we're also looking at how these management practices and the application of manure are affecting the buildup of soil carbon over time. Because this is a way that you can offset some of your greenhouse gases from your production facility is with the carbon that's stored in the soils here in the agricultural fields. And as you can see, our fields are irrigated. For those of you who are not out in the arid West, it's hard to imagine, but none of our crops grow without continuous irrigation. It's a really important feature that plays into how nutrients are cycled, the type of emissions that we see from these fields. Another thing is that when we use crops like potatoes and sugar beets in our rotations, we can't have a true no-till system because just the harvesting of those crops creates quite a bit of soil disturbance, which is pretty much the same as cultivating a field. Thank you for coming. There's been a lot of work done in these long-term studies that we've looked at, and we're just going to gloss over some of the highlights that we've found. Particularly today, we're going to look at yield, quality, and the effects on soil nutrients. If you have other interest in other aspects of these studies, please feel free to contact us, and Rob and myself can provide any other information that you might be interested in. These are the 3 different rates that I mentioned. We have a low, a medium, and a high manure application rate. and these are on a wet weight basis. Just to give you an idea of what our highest manure application rate looks like, this is really what it looks like. A lot of people see the number 45 tons per acre and they're thinking we're stacking it 2 or 3 feet deep, but that's not really the case. This is what the high manure application rate looks like. There are a lot of treatments in this study, so we tried to group these to make them a little bit easier to see. So they're grouped for the 2 low rates, either applied annually or every other year, the medium rate, either annual or every other year, the high rate, either annual or every other year, compared to fertilizer and control. These are the barley yields over the first 4 years that we had barley in the rotation, and you can see that statistically there were very few differences in the actual yields, especially between the fertilizer and the manures. Obviously these red bars are the controls where they've never received any nutrient application, so over time those yields have been going down. What we did notice, particularly with the barley, was at some of the real high application rates have a little bit of a depression in the yield, and we believe that that's actually due to lodging, and it's the inability to actually accurately or be able to harvest all the grain, because some of it's laying down and we probably lose some of it when we're harvesting. And this is one of the quality aspects of barley that most producers are concerned with. Most of the barley around here is grown for malt barley, and so you need to keep the proteins low in a malt barley or it has a negative effect on the malt quality. And so you try to keep your proteins, below 13, maybe 14%. But you do see that as we have, especially in the earlier years, as we had increasing manure application rate, our barley proteins were increasing. This year there would have been manure applied to every plot before planting, the fall before. By 2015, the ones that were planted every other year had a year off of manure, and you can see that taking a year off of manure actually reduced the protein content of the barley in those years. 2019, there didn't seem to be as much of an effect. So that's one thing for producers to keep in mind, is that as you increase the amount of manure that gets put on these plots, you can have an increase in protein, and that's something you need to watch for. The wheat yields were a little more consistent. We did see some increases in the first year with manure application compared to the fertilizer, then a little bit that second year, but by 2019 we didn't really see true differences in yield whether you use fertilizer or manure. And like with the barley, you also get an increase in protein in your wheat, but that's a good thing when you're growing wheat. And we also have been looking at the bake quality of the wheat flour, and it's been interesting that we've seen some positive influences on some of the bake quality. If you're ever interested in hearing more about that, you can just let me know. One of the biggest downsides that we saw with really high manure application rates, and that would be our highest rates, is you do tend to get lodging, which can decrease your overall yield and cause quality problems with the grain. And we're a little unsure what was happening with that, but I think what we've kind of figured out over time is that when you have manure in your system compared to fertilizer only, you have a lot more biomass that's produced with these plants. So every plant grows a lot more tillers and they have more heads. The weight that's on these stalks is quite a bit heavier in our manure plots than the no manure plots. They tend to have greater susceptibility to lodging than when we just have fertilizer. And even when we use a growth regulator, we still seem to have lodging pretty consistently in the highest rates of manure application. Sugar beets were included because there are a lot of producers that were a little uncertain how you would manage manure nutrients, particularly nitrogen, in growing sugar beets. And this is because sugar beet sugar yield and impurities are highly related to the amount of in-season nitrogen that is available, and particularly late-season nitrogen. If you have a lot of late-season nitrogen, you can end up with poorer quality in your sugar and having more contaminants, and that could translate to lower prices for producers. All the manure applications tended to have a greater yield, although these weren't always statistically significantly different. The beets tended to be a lot larger when we had manure application versus fertilizer, and the biomass produced on each field was quite a bit larger. We had larger beets, but we tended to have a little bit of depression in the sugar sometimes, particularly at the high manure application rates compared to fertilizer. And as the years progressed, this depression got a little bit bigger. But in the end, what producers care about is what they're going to get paid for. So if you look at the estimated recoverable sugar, there's not much of a difference between, say, the fertilizer and the different manure treatments. And that's because the beets were actually larger and you had more biomass when you had manure manure application, the sugar was a little bit lower, but in the end it kind of averaged itself out. So producers would have been paid the same amount of money for having manure in the rotation versus not having manure. So adding manure to sugar beets is not proven to have any sort of negative consequences in a sugar beet rotation. We also looked at potato, which is another popular cash crop in our valley here, and there was, especially in the beginning, little effect of manure on the fresh weight of potatoes from each plot. You could see over time it looks like some of the manure treatments are having a little bit higher yields in terms of fresh weight. We did see, though, which is somewhat of a negative, is that the specific gravity of the potatoes were decreasing linearly with manure application rate. So even though your fresh weights are pretty high, the dry matter produced is a little bit lower for your higher manure application rates than your fertilizer treatments. And that translates to less product once these potatoes are processed. But we did not see any effect of manure on yield or disease or most of the quality other than the specific gravity. We also have been looking at the effects of manure on soil nutrients. Of great concern to our producers here in southern Idaho is looking at how manure application is affecting the soil test phosphorus. This is because they're regulated currently by the State Department of Agriculture based on their soil test P. And in the past and the near present, the threshold for soil test P was set at 40. And you can see here's our highest manure application rate every year, and then these application rates are going down till you get to the lowest rate here applied every other year. And you can see that over the course of from 2012 to when we started applying manure to 2019, there's been a really significant increase in soil test P at the highest manure application rates all the way down to 2 feet, and we're even starting to see an increase at the highest manure application rate down to 3 feet. So phosphorus is actually starting to move through that soil profile at these high manure application rates. The only treatment after 7 years that is still below the 40 part per million threshold was the lowest manure rate applied every other year. The other treatments, even the lower treatments applied every year, are still gaining enough phosphorus that they're above what was the regulated threshold level. The biggest concern when we think about phosphorus, particularly in most of our soils, is surface runoff and erosion. So how much phosphorus is in the very top of the soil is of greatest concern when you're trying to determine the risk of phosphorus losses from these fields. If you have high soil test P and you have runoff from the field, you can have quite a bit of both particulate and soluble P runoff. We also have been looking at nitrate through the soil profile, and you can see as you increase manure application rates, you have quite a large increase in soil nitrate, even down to several feet, and we were measuring down to 6 feet, and even the fertilizer, which is the orange here, still at 6 feet is significantly greater than our control plots. So even though we try and carefully manage nitrogen on these plots and we try and do a careful job of irrigation, you can still get nitrogen movement through preferential flow, and if you over irrigate either late or early before the crops are really taking up that nitrogen. One of the huge benefits of having manure in the system is the ability to supply plant available nutrients. As you saw with the phosphorus data, there's quite a bit of available phosphorus when you apply manure, but there's also quite a bit of nitrogen that becomes mineralized over the season. So your manures really act almost as a slow release fertilizer as they're releasing this nitrogen throughout the growing season, which allows the plants to be able to continually take up nitrogen when they need it. And the higher the manure application rates, the greater this increase in mineralization over time. Manure can really do a substantial job at replacing the need for fertilizer nitrogen. One thing to be careful of, so this was back in 2017 when we had grain. We typically harvest our grain at the beginning of August, and you have to remember that even when we harvest the grain, there's not a crop on the field, that nitrogen is still being mineralized late into the fall. And so you have to be really careful how you irrigate and how you manage your fields later in the year so you don't accidentally lose that nitrogen. And being able to add a cover crop or some sort of winter cover could also help you capture this nitrogen and keep you from losing it from the fields. If you look at the total amounts of nitrogen mineralized over the season, this is the net nitrogen mineralization, how much was released from the beginning of the growing season to the end of the growing season. This was our control, and even our soils out here produce a lot of nitrogen naturally. Fertilizer is pretty close to the control, but when you look at the manure, especially this was in 2019, so you'd had 7 years of manure application at this point, you're getting close to 300 pounds of nitrogen per acre available for the plants. And so this has pretty much eliminated our need to apply nitrogen to a lot of these treatments because the manure is producing plenty of nitrogen over the growing season. And you can see that, especially at the lower rates, the biennial applications of manure tend to be a little bit lower than the annual applications of manure, but this difference has kind of been decreasing each year as we're building up soil nitrogen due to the manure. Related to soil organic carbon, and this plays into the whole calculation for your net zero. This is where we started at the beginning of the project, and as you can see, as you increase the application rate of manure, you're increasing that soil organic carbon storage. And over time, it's increasing as well. As I mentioned in the video, in years where we do have potato, so in 2014 we had potato, 2018 we had potato, and in 2016 we had sugar beets, that when you harvest and you prepare the beds to plant even, you've got quite a bit of soil disturbance. So you can see during those years there was a drop in soil organic carbon in the years where we had quite a bit of soil disturbance. But even including those crops in the rotation, we still have quite a lot of carbon stored in these soils with the addition of manure.
When applying 45 tons of manure, what is the NPK pounds per acre?
The total nitrogen is really quite high, and that's because a lot of the manure that we're using in this study is scraped from open lots, and so most of the volatile nitrogen has already been lost. We may be putting on 800, 900 pounds of total nitrogen at the highest manure application rate, but we find that only about 10 to 12% of that is actually plant available in the year that it's applied. And then over time, there's a cumulative effect of that nitrogen being available. But what we have found is that most of all that nitrogen that we've applied so far is actually still sitting in the soil profile, so we really haven't lost a lot of it.
So you mentioned that the manure is coming from some dry lot dairies. Do they come from the same source, or are these from different farms?
A couple of years they were from the same farm, and then some of the other years they were definitely from different farms.
You mentioned high, low, and medium rates. How are the rates determined?
We wanted the low application rate to be low enough that you would still have to apply fertilizer. So for a lot of those crops in the beginning, and particularly for potato, the low rate would be low enough that you would still need to add additional fertilizer to meet your crop needs. The high rate is more typical of what producers are applying, and then we wanted to pick a rate kind of in between.
Is water quality a concern with the increasing application rates?
If you have movement of nutrients off-site, it's definitely a water quality concern. A lot of the risk of nutrient loss is going to be determined by how much soil, phosphorus, or nitrogen could be moved off of that site. If it's improperly managed and you have a lot of nitrogen that can leach, or you have a lot of phosphorus that could be lost in runoff, then it has the potential to be a water quality issue.
Were there any salinity issues in your application that impact plant growth?
So far, we have not had any salinity issues, but you also have to keep in mind that in southern Idaho, we have excellent water quality. So all our irrigation water is super low in salts, and so a lot of those salts just get moved through the soil profile each season, and we don't end up with salt buildup. If you were in an area with lower irrigation water quality, that obviously could be a concern.
Question here, I'm wondering if there's an economic piece to these studies. Would love to know the cost savings, or if there is one.
This official study will end next year. Part of what we want to do is come up with really good recommendations for producers on how much manure should be used with these different crops, and we can do a little bit of a cost analysis of how much they could be saving in fertilizer by using the manure. So hopefully there'll be a little bit of an economic component in the extension publications.
In this study, is fertilizer rate adjusted for treatment?
The fertilizer rates were determined based on the University of Idaho guidelines. So we would soil test each spring, and then we would follow the guidelines to determine how much fertilizer needed to be added to all the treatments.
What was your irrigation application efficiency on your plots? How much leaching occurred?
know how much we applied, but we haven't really studied the efficiency. And quite honestly, in Idaho, we have plenty of irrigation water, so a lot of people aren't that worried about it, and we didn't study that yet.
Were other metrics used to measure soil till, like worm density, water retention?
There's a whole set of studies that are currently being conducted looking at all the different soil properties and a lot of different soil health indicators. All that data, if you're interested, will be available as well.
Was there any work done on fresh versus compost?
In another long-term study we have looked at fresh versus composted manure, and that's something that we could provide you with data if you're interested.
When and how was the manure applied?
The manure was applied in the fall before the growing season. It was just spread with a spreader and then immediately incorporated.
Did you see any changes in vegetation uptake by plants other than more tillering with the application manure that could relate to lodging?
We've got a lot of data for the barley and wheat that we still have to go through. I mean, we looked at plant uptake of everything, like every cation we could measure. And so there are a lot of things that I think we'll go back and look at and see how they relate to lodging. But we're going to start writing those papers probably the end of this year. We've been working on the potato data right now.
Do you have an increased weed issue with increased raw manure?
On these plots, I did not really see a manure effect in terms of weed pressure. When we talk about the cover crop plots next, I did see more weed pressure in our manure, especially the no-till plots, than I did with non-manure plots. These were conventionally tilled each year, so I think that helps cut down on the weed pressure.
What are the major differences in impacts on soil and plant parameters between annual and every other year application?
That's some stuff that we need to investigate a little bit more. I mean, you definitely did see when you went to an every other year application in barley, you saw decreased protein. In potatoes, it had a little bit of an effect on the specific gravity. For the sugar beets, it's not as impactful on the sugar. So, taking a year off a manure application for crops that might be sensitive to having excess nutrients is a practice that we'll probably end up suggesting for certain crops. A lot of questions we can ask, and again, feel free to email me or call me if you have specific questions along those lines too.
Hi there, my name is Robert Dungan and I'm a research microbiologist with the USDA ARS lab here in Kimberly, Idaho. Today I'm going to talk to you about these chambers behind me. They're greenhouse gas emission chambers, and specifically we're monitoring the emission of methane, carbon dioxide, and nitrous oxide. It is a fully automated system. Prior to this we used a manual gas chamber system where we could only go out and collect samples maybe once or twice a week. But with this system, we can measure emissions 24 hours a day, 365 days a year. The chamber system that you see here behind me was purchased from the Queensland University of Technology in Australia. It's manufactured from stainless steel framing, plexiglass. There are lids that close. It operates on a 1-hour cycle. Samples are pulled every 15 minutes. And with that data, we can generate a flux estimate. The advantage is we can account for the emissions much better than the manual system. And our particular interest really is nitrous oxide because it has a global warming potential that's about 300 times that of CO2. There's a couple points that I want to emphasize here. Nitrous oxide is produced by nitrification and denitrification, so that it is essentially driven by microbial activity, and as a result, things like soil moisture, soil temperature, and nitrogen availability regulate the nitrous oxide emissions. The data in the figure here is recent data using the automated chamber system. It's from the fall of 2019 through the present. You notice here that there's a dramatic increase in the nitrous oxide flux throughout this time period, especially for the higher rate of manure application. And there's a few things to point out here, especially that at this point we're in the winter and there are nitrous oxide emissions during the winter, even when soils are frozen. But here in Idaho, it's really sunny a lot. During the warmer days, we'll have thawing events, and during these thawing events, you have a substantial release of nitrous oxide. And you can see here at this inflection point, sometime in probably late January, we have a big increase in the emission of nitrous oxide. Things kind of during this time period here, when we're not irrigating, things tend to slow down a little bit, and then they'll pick up again. During the irrigation, which begins at this time of year, we don't have data points here because of field preparation. What's really interesting is that the cumulative emissions or emissions overall are dramatically higher at this high rate of manure application. And you would expect some type of incremental increase, but you just have this dramatic boost in emissions. So this is certainly an area that needs more research to kind of figure out where this threshold is to prevent having excess emissions from these cropping systems. Going back in time, this is 2016. This is the daily flux rates for nitrous oxide. This is after 4 years of manure application, and the crop was sugar beet. And the data is kind of parsed out into the winter time, early spring, and then later spring through the growing season. And I just don't want to belabor the point, but want to make it clear that there are emissions during the winter, and those emissions during the winter can be equivalent to what you find during the growing season. So it's something we need more research on this. It's something to consider. It's very important. And you'll see once again, it's driven by manure application rate. Very high nitrous oxide fluxes with the high rate of manure. When you move to the growing season, you'll see these pulses of nitrous oxide. What's driving this mainly is irrigation events early in the season. What happens is the microcytes in the soil become anaerobic, there's available nitrogen, and the microbes are denitrifying, and so you'll have these major pulses. Kind of a rough estimate would be that maybe 80%, somewhere around there, of the nitrous oxide emissions are occurring during the growing season, during this time of year. So if you could prevent nitrous oxide emissions early in the growing season, at this particular point in time, you could dramatically reduce your overall emissions. And the final slide I have here is normalized data. I think that this is a more important metric than just looking at total emissions. On the left, we have nitrous oxide emissions as a percent of total N applied. What you'll see overall is that the percent of N coming off as percent of total N applied is very low. For fertilizer, it's about 0.25%. And then we have lesser amounts coming off from the manure treatments here. I will say that this data is slightly more skewed with respect to manure because you're really applying more nitrogen with the manure application. A lot of that is tied up in organic matter, and a small fraction of the nitrogen is really available in manure. Moving on to the right, we have the data presented as an emission intensity. That is the amount of nitrous oxide coming off per crop yield. In this particular case, it's metric ton of dry matter. We have the 4 different crops from the beginning of the study here: wheat, potato, barley, sugar beet. You do have an incremental increase under wheat of the emission intensity, with the greatest emission intensity occurring under the high rate of manure. Under potato, things kind of start falling apart here, but you do have a really high emissions intensity under the high application of manure. But this data, as April alluded to a little bit earlier, is skewed because the potato dry weight is much lower at the high manure application rate. And then emission intensities are somewhat similar under barley. Under sugar beet, they're much lower. But I think the point here is that you need to pick a manure application rate that produces a much lower emissions intensity.
In the video, you showed the chambers. Were those chambers installed in every replicated plot?
No, we only have 12 chambers. We pick for the treatments in the study.
What was the temperature delta between inside the testing apparatus and the net ambient conditions?
I have the data, I haven't parsed through it, but we have specific settings for the chambers that will open the chambers if they become too hot. They go above a certain threshold temperature, they will open. At this point in time, for an hour-long sampling period, we haven't had that situation occur.
Based on progress with your field experiments, what are the potential agronomic options for farmers to mitigate nitrous oxide emissions when they use manure as a soil amendment?
The lower the rate of manure, you could help mitigate your nitrous oxide emissions.
The huge differences between emissions with the greatest manure application rate and irrigation events may be related to affinities, KM in parentheses, of enzymes involved in the denitrification process. Is that something you plan to examine?
That's probably delving in a little bit farther than I'm going to go, but it's certainly something to consider.
Do you have a sense for how gas data using continuous measurement compares with manual collection with interpolation?
You know, at this point, I haven't compared the two systems, but from the data I've seen so far, the numbers are pretty darn close.
Not sure specifically what this is referring to, but the fluxes measure all through the year or just during the crop growing season?
When we were using the manual chamber systems, we were mainly doing this during the growing season, but now we run the chamber system all year.
This study consists of the treatments of either having manure versus fertilizer with and without a cover crop, and either under conventional tillage or under what we wanted to be no-till but eventually turned into minimum till. The manure application on these studies was matched to be the same as the high rate on the long-term manure study. And our goal here was to look at the different treatment effects on nutrient cycling, change in soil carbon over time. We'll eventually look at greenhouse gas emissions from these fields as well, and really trying to look at how we can maximize uptake of nutrients from fields and maximize our forage production at the same time. We had some challenges with these plots initially. This was supposed to be a no-till treatment, but unfortunately due to compaction, over time we were having trouble with the planter. So we had to switch to minimum till, where we're strip tilling in the corn each year. Other challenges that we've had are due to weed pressure. So in the plots that do not get any tillage, even the fertilizer and the manure, we tend to get a lot of weeds in those plots. Having the manure in a no-till system presents another challenge because that manure sits on top of the soil surface and forms a pretty thick layer over time. Other potential challenges with the no-till system is having that manure sitting on the surface can be an issue when we deal with things such as runoff and nutrient transport. Since that manure is right on the surface, it can be lost with surface runoff and end up directly in water bodies where we don't want it. We're going to hit just a few highlights from the cover crop study. One of the most dramatic things that we've seen with this study is the production of the cover crop, which is triticale, and the effect of manure. These are broken out, these small bars. The first two are the no-till system, which is really a minimum till now, conventional till but without manure, and then we have the no-till and conventional till but with manure. And you can just see in a good year where we were able to get the crop established early enough that the effect of manure on your yield is just dramatic. You're getting, in a good year, over 14 tons per acre from the triticale when we had manure, whereas when you don't have manure in the system, it's been less than 3. Most times this year we got a little bit close to 4. But it can be a little bit tricky, so in 2018 we did not get the cover crop planted early enough, and so our yields were so small in the plots that we really couldn't harvest them very well. They were a little bit low, obviously, with just the fertilizer plots, which makes them challenging to harvest. In terms of the effect of the cover crop on silage yield, so in 2016, this is before we had any cover crop in the study, and you can see our yields were about 28 to 30 tons per acre, which is a pretty typical yield for southern Idaho. But when we did incorporate the cover crop into the study, we did see a drop in overall silage yield. This year was a little bit better. We were closer on average to about 25 tons per acre. But when you add in that triticale, if you include both of the forages in your overall tonnage, you can still increase your overall production from close to 30 to up to 40. So you're still getting a 10 ton per acre boost in overall forage that you're pulling off those plots. And this is just to point out, this is a little bit of an unfair comparison because of the size of the plots and everything. We do have to plant the corn at the same time and harvest it at the same time. These numbers, if you weren't using the cover crop, would have still been closer to 28 to 30 tons per acre, so just keep that in mind. And this year we've switched to a real short season corn to see if we can increase the yield a little bit by using a short season corn as compared to this, which was a more traditional silage corn variety that we were using. This is the soil organic carbon, and I split this up to hopefully make it a little bit easier for you to see. Over here on the left, these are the plots that have manure, and so the conventional till are the green ones. These second two, more of a brownish color, are from the no-till plots. And then over here on the right are the treatments when you don't have manure. Right off the bat, you can see the dramatic difference that you have when you include manure in your system on the overall soil organic carbon. And that carbon's been building every year with manure application. What we don't see is much of an effect on using conventional tillage versus no tillage, or having a cover crop or not having a cover crop. And you can see this really clear over here, where there's basically no effect of tillage and hasn't been any effect of just including the cover crop on the soil organic carbon over time. In our system, adding manure has a dramatic effect, but using some of these other conservation practices, such as no-till and cover crops, has really had minimal to no effect on the soil organic carbon storage over time. Some of the challenges that we had with the no-till were we had increased weed pressure. So here we had manure in the no-till system. This was the fertilizer. We have accumulation of manure on the surface. It's a little bit hard to see here. This year was the first year we had kind of a late emergence in these plots where we had no-till with manure, and I wasn't sure whether it's due to salts, whether it's due to some sort of crusting with the manure. And I looked at the water data lately, and I think part of it might be due to the lower water volumetric content in these soils where we had manure and the cover crop, because the cover crop did so well, it really used quite a bit of the water. I'll be curious to see whether those plots catch up in terms of yield at the end of the year.
Is the harvested triticale, is that ensiled for dairy cow feed?
We don't have the ability to ensile it ourselves, so we're just green chopping it and removing it. But it could be green chopped and fed, it could be ensiled. It would be up to the producer to decide how they wanted to manage that when it was harvested.
Typical harvest for our dairies is to green chop it and ensile it.
Were there any forage quality parameters measured in silage corn?
Yes, we've been measuring all the forage quality each year, and if you're interested in getting some of that data, I'd be happy to share it with you. Just send me an email.
Was there any soil carbon fractionation, the work done other than measuring total soil organic carbon?
We have not done any fractionation work yet. We've talked about doing that. It's basically a lack of manpower at this point, but that's something that we've definitely been thinking about doing.
If the cover crops were grazed, how does it help increase soil carbon stocks?
One of the things that helps build soil carbon when you have the cover crops, although as I pointed out, we're not seeing a huge effect in our soils on just having cover crop, but you do end up with root biomass that's left in the soil afterwards, and that could contribute to soil organic carbon over time if it's resilient.
We're saying that nitrates stay within the soil profile even when you add the higher manure rates. What are you seeing from the groundwater well monitoring? And have you seen any movement of dissolved phosphorus and being monitored in nearby streams and lakes?
In these plots, we have not had the resources to try and actually measure leaching. So what I've done, and these are really deep silt loam soils, they're like at least 10 to 15 feet deep, which you may not typically have on a lot of ag field. We've seen the nitrogen and the phosphorus kind of move down through the soil profile over time, and I've done kind of a mass balance to look at what we've added, what's been removed by the crops, and what's still there in the soil. And at the moment, you can see that that nitrate's definitely moving down, but it seems like it's still at this point within the zone that we're measuring. But obviously over time, as that nitrate gets below the root zone, it's going to keep going deeper and deeper in the soil and eventually be lost. We have another study that's set up to specifically look at leaching of nutrients, and we have a little bit of data from it, but it hasn't been in place a really long time. So if you're interested in some of that information, again, feel free to call me, email me, and I'll try and provide you with some of that data. I'm April Latham, and I work for the USDA Agricultural Research Service. And back in 2005, we started doing air quality work related to animal production throughout ARS, and we were one of the locations here in Kimberly, Idaho, that was chosen to start doing this type of work. We've been working on approximately 4 different dairies throughout southern Idaho and 2 dairies in California, where we've been trying to look at whole farm emissions and really understand what type of emissions you get in the different source areas on a farm. So looking at the animal housing, looking at manure handling and storage, looking at support animal housing, and long-term storage of manures. And so we tried to do several different types of facilities that were common to southern Idaho and the western US, which is quite a bit different than dairy production in the eastern and midwestern regions of the United States. We tend to have more open lot dairies. We have some freestall dairies, but the support animals are still on open lot dairies. Most of our manure is either handled as a solid and composted, or some is just stacked. Or we also have some dairies that will have a significant amount of their manure stored as a liquid in a lagoon type system. And even on the open lot dairies, there's always manure that comes from the milking parlor that's stored in the lagoons. So we put a lot of time and effort into picking out the dairies that we work on. They have to be fairly well isolated in the landscape in order to feel like I'm getting a really good estimate of emissions from the farm. So we tend to pick dairies that are isolated or at least don't have a lot of sources of methane or ammonia upwind from them. And I also try and pick dairies that the layout of the dairy itself, where they have the housing and where they have manure storage, tend to be in a way that's perpendicular to the wind, so that I can do a really good job of isolating the different source areas on the dairy to make sure that we're getting really good representative emissions numbers from those different sources. So at the dairies, we focus on measuring ammonia, methane, and nitrous oxide from the different source areas. And the equipment that's behind me is the equipment that we use at the dairies. We have multiple units of these. They are called open path FTIRs. And so what they do is they pass a beam of infrared light from the detector here to a retroreflector that's behind me, which bounces back into the instrument, and it's measuring the concentration of these different chemicals within the path length, which is really nice because it allows us to get a better average concentration from a larger area in the dairy than you would if you were just measuring at a point source. And so then the data that we get with FTIRs, the concentration data, is then matched up with weather data that we get using a 3D sonic anemometer, as well as your basic temperature and wind speed monitors. And we combine those two and we use modeling to estimate an emission rate from each of the different sources. To get an overall measurement for the farm is we add the different source areas together to get the total emissions from the whole farm area. There are quite a bit of differences in emissions throughout the year, especially here in southern Idaho. We have very distinct seasons. So your emissions are going to be different in the summertime when it's hot and dry versus in the winter when it's cold and the ground could be covered with snow, or the lots are frozen and the lagoons freeze over. One of the unique features of dairy production in the western US is that a lot of our dairy cows are housed in open lots. And so these are open corrals with dirt floor and then usually a concrete apron. And the manure from the lots are harrowed in the summertime, or some guys sometimes they'll stack it up into smaller piles within the lots. In the wintertime, they tend to scrape the manure and pile it, and they also tend to use straw bedding a lot of times for the cows during the wetter months, which also gets scraped and piled in the lots. So you have a manure source in the lots that is producing ammonia, methane, and nitrous oxide, and then you also have nitrous oxide being produced from the soil within the lots because they're continually getting manure and urine applied, and nitrogen builds up over time, and then that nitrogen can be denitrified and lost as nitrous oxide. The lots also tend to be the largest source of ammonia emissions on the farm because the cows are urinating on the lots, and then that uric acid breaks down pretty quickly to ammonium, and then it's lost as ammonia in a very short period of time. Manure that's deposited on the concrete aprons behind the feed lane is either scraped and piled in the lots sometimes. There are some dairies that might vacuum that and put it into a pit that'll eventually end up in the lagoon. And there are a couple dairies that actually flush those aprons to remove manure from the lots. And then typically what happens at the end of the season, they'll clean out all of these lots, and lots of guys will take it to a compost yard and they will compost it, and then that compost eventually gets land applied. But not every dairy composts. There are some dairies that will just clean it out, stack it as a solid, and then that manure will be land applied in the fall. On a typical open lot dairy, your largest ammonia sources tend to be from the lots, and then your second largest sources can be from the composting area and then the lagoons. When we look at nitrous oxide emissions, the largest emission sources on an open lot dairy tend to come from the feedlot, dry lots themselves, in the composting area, and then we actually do get a little bit of nitrous oxide emissions from the settling basins when they form really thick crusts. When it comes to methane emissions, it can be evenly split sometimes between the enteric methane emissions from the cows themselves and the housing area. And then one of the other biggest sources that we found is these small settling basins where the volatile solids contents tend to be really high, and they generate quite a bit of emissions before the lagoon water then flows into the lagoons, and then the lagoons are another additional source of methane emissions. Although we're not at a freestall dairy, we have done quite a bit of work at freestall dairies in both Idaho and California. And the emissions are a bit different when you're at a freestall dairy. The methane emissions tend to be pretty large from the barns themselves where the cows are housed, but then a secondary, very large emission source tends to be from the settling basins and the lagoons as well. We don't see as much nitrous oxide from freestall dairies, a very minimal amount from the housing area when the manure is moved quickly out of the barns, but again, we do see nitrous oxide emissions from any stored manure that is on the facility if they maybe separate their solids and do some composting, or we definitely see some again from the settling basins when they form really thick crusts. The ammonia emissions from freestall dairies tend to be about evenly split between the housing area and the lagoon system, because what's not lost from the housing area when it's immediately excreted tends to be flushed or moved quickly into the liquid storage system, and then that ammonia just tends to be lost from that section of the dairy instead. Many of the dairies that we work on have their own support animals on the farm, so that's included as part of the whole farm emissions. So for a lot of our dairies out here in the western US, calves are started in hutches, and then they tend to move to group pens and eventually to open lot areas. And the dry cows are actually usually housed in open lot areas as well. So that's a big difference from freestall dairies or dairies where they may not be raising their own replacement heifers on site, and these emissions are also included into our overall calculations. We have two slides that kind of show some of the results from the emissions work, and this is focused on just the greenhouse gas emissions. If someone's interested in the ammonia emissions, we can provide information on that as well. I just gave 4 examples of 4 different dairies that we've worked on. This first one here at the top is a small open lot dairy, and I've tried to break this out by where on the dairy you see these different emissions. For methane, you can see that the majority of methane is coming from the lots, and that would be enteric methane. From the cattle, a little bit from the calf pens, which is probably from the bedded pack mostly, and a little bit from enteric, but not very much enteric at that part in their life. A little bit from the lagoon, and this other big chunk comes from the settling basins. And again, that's because when they form a crust, you can end up getting denitrification of nitrogen in those crusts, which then gets volatilized, and then a little bit lost from the compost. And we also get nitrous oxide from the lots, as I mentioned, from the soils in the lots, and then when you compost the manure, or anytime you have stacked manure on the farm, that can lose nitrous oxide. And I also wanted to show this on a global warming potential, because it's really easy to, in some cases, dismiss this nitrous oxide because the bars end up looking really small from your different source areas. But you have to keep in mind that the global warming potential of nitrous oxide is close to 300, and methane is only about 28. So when you multiply those out and look at the total global warming potential, you can see that on an open lot dairy in particular, you can have a really large piece of your overall global warming potential coming from nitrous oxide on the farm. In this particular farm, the GWP was about 3.5 pounds per gallon of milk. You can see how these different source areas are contributing to both the methane and nitrous oxide carbon footprint on the farm. This farm below it was another farm in Idaho. It was a freestall, but the cows actually had access to the lots as well. And this farm had an anaerobic digester. And you can see that the methane was pretty much evenly split between the enteric methane in the barns and the lagoon system. There was some nitrous oxide from the lots in particular, and then a little bit from the lagoons. And when you multiply this all out, you can see the global warming potential contribution from these different source areas. And this one was a little bit higher overall GWP per gallon of milk. But I should also point out that this particular dairy had some areas where they had support stock and dry cows on lots, which were not included in this calculation. We did not include methane leaking from the digester, and there were a few other areas that probably are producing methane and nitrous oxide that we were not able to measure on the farm. This value is probably, in all reality, higher than 6 pounds per gallon of milk. And these two dairies were actually dairies that we worked on in California. One was an open lot dairy, but they used a flush system, and they also had some animals in a barn. So when we say barn here, that's really the barns and the open lots. It's just the housing area. The majority on both of these dairies of the manure is handled as a liquid. And you can see when you handle manure as a liquid, you really see these large amounts of methane emissions coming from that section of the farm. And in both cases, it was greater than the enteric methane produced by the cows. And you still did get a little bit of nitrous oxide from the barn area, the lagoon, and the settling basin. And again, I mean, when you're doing this research, there's not a lot of research looking at nitrous oxide from production facilities, and it looks really small, but when you multiply it out to the global warming potential, you can see that this can contribute a pretty large chunk of your whole GWP per gallon of milk. So here they are again, the methane and nitrous done on a global warming potential. This dairy was about 14.5 pounds GWP per gallon of milk. And the freestall dairy, very similar. Again, that's because both dairies were storing most of their manure as a liquid. You see these really large losses, particularly from the settling basins where they have a high concentration of volatile solids, a little bit of nitrous oxide from each of the sources. And again, this dairy was slightly higher, but only 14.5 versus 14.5 pounds CO2 equivalents per gallon of milk.
Could you please explain the difference between a lagoon and a settling basin?
What we're calling a settling basin is most of our liquid handling systems are set up that the fresh manure will flow into what we call a settling basin. And they tend to be long, skinny cells. They're usually quite a bit smaller than the lagoon. And the purpose of those is to capture as many solids as possible, and that the water going from the settling basin into the lagoon has a much lower solids content. It makes it easier to clean out the solid manure over time when it's more concentrated in a smaller cell than having it in your main lagoon, which is where you're going to irrigate, that liquid and send it through your pivot. So it's really used to capture solids.
What is the source of methane from the lots?
From the lots, it would be enteric methane from the cows. In the springtime, though, we have noticed when there's a lot of really large piles of manure, especially with straw, and things are warming up in the spring, those piles will really start to cook, and you can get an extra amount of methane coming from that manure storage inside the lots in addition to the enteric methane.
What new practices can be done to reduce emissions from the dairy lots, piles of manure, and lagoons to help strive for a net zero emission dairy farm?
That's something where we need a lot of research. Most of our research up until now has just focused on getting baseline emissions data from actual working dairies and really getting a good understanding of where emissions are coming from, figuring out how we're going to mitigate, particularly nitrous oxide emissions, is a challenge that we're going to need a lot of future research on. There has been research related to enteric methane emissions and how we can reduce that. If you look at manure, the methane emissions from manure storage, if you separate your solids, any solids that you can keep out of the liquid system will decrease your overall methane emissions from the manure storage part of your facility. And those are the things we know right now that work really well. I think everything else is going to be developing new technologies to capture more of those solids, maybe capture more of that nitrogen so that we can reduce the overall emissions of both methane and nitrous oxide. But that's an area that we need to start working on next.
How large of a reduction of methane emissions from settling basins do you expect with previous solid separation?
We don't have on-farm data on that, and it becomes difficult to kind of get on-farm data because no two farms are the same, so it's really hard to compare one farm versus another. The two farms that we looked at in California, they both used a flushing system, although one was open lot, but when we looked at the open lot had a screen separator, so it was separating out some of the volatile solids. And when we looked at the amount of emissions on a per head basis, it did look like there was maybe a 20 to 30% bona fide reduction in methane emissions from the liquid storage when they were using the solid separator. But there's been very, very little data collected on farm that's really evaluated these mitigation practices to see what the true on-farm potential of these different practices are.
Thank you for joining and for sticking around late with us, and we hope you have a great rest of your day.